Okay, verify you see title screen, please. And you see my
I
mousey.
can see it.
Yeah.
Very good. Okay, so this is our final unit of brakes. Unit 5 is ABS, which includes vehicle stability control and even a little bit more than that. So we could kind of summarize it as like electronic braking, which would also include regenerative braking, and Toyota has a whole lot of different uh, systems and features that are tied into ABS, VSC, is electronic stability control. So we got a lot of stuff in there. So without further delay, we're going to start with ABS specifically out of all those. And do you remember this from Unit 1? So I forget who we picked, but somebody was playing with the basketball and they went out in front of the road with it bouncing and they were worried about getting run over. Well, um, this, we tied that to several different um, brake systems, right? Even just the hydraulic system, disc brakes, the drum brakes, all that stuff leads and the booster that would all be of concern in a situation like this. So now we're coming right back to where we started. We need this vehicle to stop. We need it to stop quickly, predictably. We don't want extended stopping distances. We don't want any sort of inconsistencies with like a brake pulsation or a brake pull, right? The system should be in good operating condition because you never know when this is going to happen. And that's really the way that you should look at it is, we're not shooting for like good enough or close enough on customer cars. So all that combined with ABS should give us a good predictable stop. And not only that, we'll get into it a little bit more. Back in the day, if you encountered this, the typical person's first response would be slam on the brakes super hard. Now you slam on the brakes really hard, those tires are going to lock up, and actually locking up the tires totally stopped is actually going to extend your stopping distance, and you're going to hit this person. Now, who is this person again? I forgot.
Mitchell.
Mitchell about to get run over. And so hopefully, who is driving? I don't recall.
Robert.
Oh, Robert's, he's probably off the brakes right now. He's probably on the gas pedal. All right, let's say if Roberto was properly trained, he would actually right now he'd be pumping the brakes. So back in the day, they train the drivers, yes, pump the brake pedal, lock them up, release them, lock them up, release them, lock them up, and that would actually give us a better stopping distance. So we didn't have the tires totally locked up solid, and the liquid, the rubber touching the blacktop liquefied and sliding out of control. So you'd say pump it, but that's probably what your parents or your parents' parents were taught. Some of you are pretty young. Parents are pretty young. I wasn't even taught that. So, when I started driving, ABS was already pretty normal. So you don't pump them anymore. ABS pumps them for you is basically the short answer. And we'll get even a little more detail. So basically, without ABS, there's some limitations. The first generation, what we call the EBC as electronic brake control, was just basically anti-lock brakes. Anti-lock brakes was exactly what we were talking about. Before, if you punch the brake pedal and held it, they'd lock up, and you were supposed to pump it, and so instead, ABS pumped it for you. So you could just tell the customer, "Don't worry about it. Just slam on the brakes. ABS will take over." And then that kind of has evolved and improved and grown to some of the more advanced things like vehicle stability control. So ABS is just anti-lock brakes. It has nothing to do with traction control and stability control. So we're just focusing on anti-lock brake systems. Now, ABS uses a computer. Duh. Hopefully you knew that. and monitors the speed of each wheel as the brakes are applied. If one or more wheel locks up, the computer sends electrical signals to the solenoid valves, and it'll momentarily hold up or release hydraulic pressure. So it can hold it, it can release it. It can basically override what you're doing with the pedal. Kind of makes sense. So if you're in panic mode, that's fine. This computers don't go in panic mode, generally generally speaking, unless you have too many tabs open. But computers do what they're supposed to do. They don't get emotional. So when the driver's emotional and they're pushing on the brakes so hard, the tires are locked up and sliding. The computer says, "Nah, let me manipulate what we're doing on the brake system," so it can actually modify the brake pressure. Now we'll look at an image here. So without ABS, we'll start with without ABS. Roberto is driving. Mitchell's coming out in the road, or in this case, some other car. Without ABS, you're gonna punch the brakes. The tires are gonna lock up. At that point, picture your steering wheel. You're locked up. You steer left. Where do you go? You steer right. Where do you go? You're pretty much gonna go straight. It's hard to get those front wheels to steer the car when they don't have traction because they're locked up, sliding. So ABS is going to do something for us beyond just hopefully shorten our stopping distance. It's actually going to make sure the front tires aren't locked. So that way, a person's natural inclination, if this car is coming on the right, like this image, they're going to steer away from it. So they're going to step on the brakes, which is gonna slow down, but not lock the tires up, at least not much. And it's still going to steer. So with ABS, as you can see, that avoided a collision. That's what this is all about. Keeping the car under control and avoiding a collision. So there's your image of what ABS looks like. And then just real briefly, go ahead, Roberto.
I was gonna ask, isn't that what traction control does though? Because I was reading and I remember it saying some traction control does basically the same thing.
Yeah, this is very normal. So this book does a good job of explaining the details of the different systems, but it's my job to come through and explain the overall, right? So perfect timing on that question. ABS is anti-lock braking. So when you're braking, it's anti-locking the brakes. Traction control which came after ABS, is more about when you're on the gas pedal. So if you're on the gas pedal, you're not anti-lock braking, right? Because you're not braking. So it is going to use the same inputs, which would be sensors. It's going to use the same outputs, which are the control valves, but it's really for when you're punching it. So I give you a perfect example. I worked with a guy, and in the dealership, he had a Pontiac GTO. I believe it was 2005. Blue. It was a nice car. 6-speed manual, sounded good. That was back in the day when it was a LS1, which is a 5.7 liter. Good horsepower. Three something, 300 something horsepower. Used to be big numbers. But he went ahead and he did quite a bit of work, installed a bunch of performance parts, and everybody was really excited because he started it up at the shop, and he went out in front of the dealership, and he planned on, you know, what I'm saying? He was gonna put on a show. He was gonna do a big burnout. What else could you say? He was gonna light them up, as they say. Um, and he put it in first, and he revved it up with the clutch down, right? And then he let the clutch out. And you know what happened? You think it was impressive? You think it was impressive? It went like this. And then it took off, and it was like, everybody's like, "Oh, seriously? We all came out here for that? It barely even screeched the tires for a quick second." And now I knew what he did. It's my job to know what he did. But the salesman and everything, I mean, the dealership cleared out. These are back in the good old days. The dealership cleared out to watch the details. And we're thinking like, oh, that sucked. That car doesn't run that good. But he forgot to disable the traction control. So the traction control will actually cut engine power and potentially apply the brakes in some of the later systems to keep the car under control. So if you go to do a burnout and it stumbles and falls on its face, like the homie at the dealership, that's traction control. If you go to jam on the brakes in the case of, someone pulling out in front of you, that's ABS. But see how they're kind of tied, but they're different. So that's my job. And then as we go a little bit further, we're going to look into what we're looking at isolation valves. And so before we would just dump brake pressure. Isolation valves are basically added, and that's going to help the driver, with these acceleration issues. This system wasn't designed to make you look lame when you're trying to do a burnout in front of your friends. It's more like picture you're in the snow, you're in the mud, you're in the rain, and it's slippery. It's designed to help the customer maintain control of the vehicle, right? So that's kind of what we're looking at. Not everybody lives in Southern California. Okay. And as we continue, so here's an example of traction control. And this is a little bit of a more advanced example, and Toyota actually does have several different things they do with traction control and ABS. But this one, for example, we can use traction control to simply cut power, like we did with my friend with the GTO, or we can actually get a little bit more advanced and use traction control to gain traction. So if this right front tire is spinning, we're not moving. And all the torque on a typical open differential is going to go the path of least resistance. So all of our torque is going over here to the right front. Now we could use those same types of components as ABS in a later and more advanced version of TCS and actually apply the brakes to the right front, which will make this more resistance. And therefore the torque will actually transfer over to the left front and actually get you unstuck potentially. So the basic overall is ABS goes along with TCS from this point out because we're looking at the same sensors, the same controller, but we use it differently. ABS is only when we're braking, and TCS is only when we're accelerating. Cool. So that hopefully clarifies not only your question, but helps everybody understand as well. So we go a little further. We even get into a next generation of both ABS and TCS has become we get into electronic stability control. And so right here, I think basically is the time where we need to talk about sensor information regarding the driver's directional intent. And that's one that's gotten people stuck. So in the book, this is actually a totally separate chapter. I bundle it all together as a package. So this is saying basically, let me convert it for you. Which way the driver's pointing the steering wheel, basically, that's what it says, right? If somebody wants to go left, they turn the steering wheel left. So we're going to take that as an input and we're going to compare it to sensor information regarding the vehicle's actual direction. So this is a system that's going to say, where do we think the driver's trying to go? And compare that to where is the vehicle actually going. So here's a perfect example. Understeer. An understeer condition is you're coming around a turn and basically you're intending to do the black arrow. You're intending to stay tight to this turn. The actual is the blue, right? So as you're trying to turn a hard, tight left, the car's kind of like, nah, I'm going to plow and go wide in the turn. And this is the guardrail you hit on GMR. Okay, that'd be an example of understeer. Kind of makes sense. So push or plow, that's kind of what it's doing. A higher level electronic stability control will actually help you not have that happen. Exactly what it does, I'm going to tell you the flat out truth. I don't really know, the engineers who design it know. So the customer never comes in and says, "Oh, my car's pushing. It's loose in the turns." That's not what they say. They're going to come in, and if there's a problem with the system, it's most likely going to have a warning light. So we don't normally get into exactly how the system functions. What I can tell you though, to make you a well-rounded technician, is if you're going around this turn to the left and it starts to plow to the right, I'd imagine they may actually start to do some braking, especially like on this left rear wheel. That's going to try to slow this down. They might actually do some braking on both of the inners to try to get the car to sort of rotate more. But if you really want to know exactly the intimate details of this, that's what the engineer does. So while it's never been my job, well, as some of the people I've talked to, some of the engineers and corporate people, a lot of times what they'll do is they'll have an expectation, they'll do some measurements, they'll have some measuring equipment, and they'll basically write a program and upload it into the control module and have it, maybe squeeze this brake a little harder, and then they'll go drive it. And if it was better, then they'll maybe have it squeeze it even a little bit harder. And if it got it even more tight, then they might go a little bit harder. And then all of a sudden, if it's too hard and it starts to get sloppy again, then maybe they'll back it off, right? So some of this is a little trial and error, and they basically write a program that's going to make the vehicle handle the best it possibly can with the computer assisting. So like, here's another example. This is an oversteer. So now you're actually trying to keep that nice left, but not super tight. The oversteer means it's actually turning more than you want it. So at the way that you'd figure an oversteer, that's basically drifting. A minor drift would be an oversteer. A major drift, all of a sudden you're cool. You see, so oversteer is definitely way cooler. A rear wheel drive car would be more prone to oversteering. A front wheel drive car is more prone to understeering. The later and greater systems are designed to deal with both of those and help both of those. And so the engineers who write that programming, they do a lot of calculations, stuff way outside of my area of expertise, and they upload the software and then go drive it and make sure everything is good. And then later, what we get into, you may even have different modes you can put it in to make it handle different, and that may be starting to already make you think some of the cars you've seen. So if it were me, I'm a little more old school in that way. I kind of want a car where I get to know the car. I want to feel if it oversteers or understeers. I want to kind of control it using, more gas, more steering, less steering. But if all you want to do is be the fastest, then you get the latest and greatest car that'll basically do it for you. So it's outdated now, but I would always pick on the Nissan GTR. That was a car you could be a ding dong and jump in a GTR and beat just about everybody. To me, it's a gamer car. That's someone who just wants to have the fastest car, doesn't want to be real in tune with the car, doesn't necessarily want to really know the car. They just want to make sure they win. So that's not really my thing. I kind of see myself more as wanting to be a little more old school, but I gotta tell you, some of these systems are pretty amazing. So, like our Camaro, it's a ZL1. It's was top of the line in 2017, and they haven't really updated the car, but I'm sure they got some much better systems now. That car is wild. Like, when I'm driving, it feels like you're going slow, and it'll just be dead flat in the turns. It doesn't oversteer, it doesn't understeer, it just sticks. So I really appreciate some of these, but I'm kind of half in and half out, I gotta tell you. So let's jump into the ABS, for example, components of a very overall view. Here we've got the four wheels, we got the brake lines going to each, but you're also going to notice we've got what we're going to call the hydraulic control unit. there's two parts here. We've got the hydraulic control unit, which is the valving. It's the actual valves that open and close. And then we have the electronic brake control module. That's the computerized part. That's the electrical part. The electrical part controls the mechanical part. So the EBCM right here, electronic brake control module, actually controls the hydraulic control unit. So they work together. They generally are replaced together, but you can, in some cases, replace one and not the other. It's kind of interesting. But again, ABS is designed to prevent the wheels from skidding, maintaining steering control if it's in a later version, and reduce stopping distances. You'll also notice a couple other things. It's got the master cylinder, the power booster, but it's also got a brake switch and wheel speed sensors. We're going to get more into those. So here's a good diagram. This is a Toyota specific diagram, and you'll notice immediately there's some differences. The brake actuator, that's Toyota's name for it. So everything I just told you about the hydraulic control unit, that's true, but Toyota calls it the brake actuator. So we call it the brake actuator. And then that electronic brake control module, that's actually a GM term. So EBCM is more of a domestic thing. Toyota calls it the skid control ECU. They both make sense to me. The skid control ECU is literally controlling skid, and it's an ECU, in other words, electronic control unit. So Bing chillin', no problem. And then additionally, you can see these arrows. Something very interesting about these. Some arrows are pointing into the ECU, and some arrows are pointing out of the ECU. So let's take one at a time. Let's go with the wheel speed sensors right here. This one, right front. Into the ECU. So that's actually an input. Now, basically, when we start talking about inputs and outputs, it's going to seem a little bit foreign, but pretty quickly, you're going to start to understand. So an input would be essentially a sensor. It could be a switch maybe, but overall, we're going to consider it a sensor. Now, your body has inputs. Can anyone come up with at least one input that your body has? Sight would be good. Smell, taste, hearing, feeling. So those are inputs that they go to our brain through our nerves. So if you think about all the inputs, those are essentially our inputs are kind of like a car's inputs. So like right now, I can see if something was flying at me, my eyes would send a signal to my brain, and my brain would process the information. Now, this system is not quite AI. It's much more computer kind of logic. It's basically, let's say that you have a wheel speed sensor, your wheel speed sensor is reporting. We're going to have 4 of those reporting at once. If 3 of them are reading 20 miles an hour and one of them is reading 0, those are all inputs. The sensors don't think, right? It's just saying 20, 20, 20, and 0. However, that's all being reported to the skid control ECU. The skid control ECU is the logic. The skid control ECU makes decisions, and the skid control ECU is going to look at that. And what do you think the skid control ECU is going to think? 20, 20, 20, and 0. The zero's on the left rear. That's the lockup. That's a skid. This car's in a skid. The ECU is not going to be emotional about it. The ECU is just going to say, I have programming instructions. And basically, kind of like you. Like, if I threw something right now, you look at me real quick. If I threw something and you see something flying at you, your eyes don't think, your eyes send a signal to your brain, and your brain is like, oh, there's a flying football at my face. What do I do? You tell me. What do you do? Smile and let it hit you. Yeah, you could. More than likely, your brain is going to send a signal to your muscles, and it's going to say like deltoid, contract, bicep, contract, whatever these muscles are, do this. And it's going to like catch the ball or knock it away or something. So that's your brain controlling an output. Your outputs would be more like your muscles, breathing, moving, these types of things. If you look at this arrow is going output. So this one's just the beginning. This is going to get way more in depth, but the only output in this one shown is pretty much the ABS warning light and technically information going to the DLC3, which the DLC3, that's where we hook up the scan tool. That's interestingly an input and an output. That's really more of communication line. But if you just think about the system, we've got inputs reporting to a processor, which is the ECU, and then the processor's controlling outputs. And in the ABS system, those are mostly going to be the valves that are going to block off or allow flow. So it's a good system. It makes sense. Engineers are brilliant, but they didn't just like mysteriously come up with this. They're copying the original engineer, which is like your body. Makes sense? So we're really kind of imitating here. Like, oh, I know what we'll do. We'll have a brain, and then we'll have sensors, and then we'll have muscles. Pretty much how you got to look at it. That's how it works. All right, so we'll continue. You also notice the stoplight switch is an input, and the brake fluid level switch is an input as well. There's going to be some more as we go. Here's an example of that unit. The silver part is the HCU. That's the hydraulic control unit. This is where the valves are. Kind of the giveaway is the lines. So if we have two lines coming in, and typically we will have two lines coming in and four lines going out, but let's just say if we just look at 2 and 2, if we have a line going in and a line coming out, that means basically we push on the brake pedal, we send brake fluid in, but the actual valving in here determines if the brake fluid ever makes it to the wheels. The brake fluid may or may not ever make it there, period. And so that's basically how this system works. We'll get in more detail. And then if you look right here, this would be that electronic control unit. So EBCM in the original terms, the generic terms, Toyota terms, this is the HCU, or this is the actuator, and this is the skid control ECU. Okay, one and the other. The processing occurs here. We know that because the wire harness goes up there and there's a whole big old bundle of wires. A lot of the wires are going to be power, ground, CAN communication, and a bunch of inputs. Brake switch, brake fluid, wheel speed sensors, and then some of the wires are going to be outputs. But generally, the output's actually just going to be right here because we have solenoids that control valves right here. So there's valves that are sticking out and a solenoid goes around it to magnetize it to open or close it. So most of the outputs in the skid control or the EBCM are right in the unit itself. They're right there. All right, cool. So we go a little further. So that's the EBCM like we talked about. Sometimes they can be separate. And then basically like what I was saying, it receives inputs from ABS sensors, compares these data to information stored in its memory. And now just a second. It's kind of interesting if you think about it. So that computer has a program, right? No one had to tell you, hey, when the football is flying at you, put your hand up. You don't want to block that, right? So just consider that. It's kind of similar. An engineer wrote a program saying, hey, if you see 20, 20, 20, and 0, that means lockup. I want you to do this. I want you to activate the valve for the left rear wheel and lower the pressure. And if we lower the pressure to that left rear wheel that was locked up, we reduce the braking, squeezing, what's going to happen? It's going to regain traction. It's going to regain traction. If it regains traction, we're good. But it doesn't stop there. It's constantly watching all four of the sensors, and it's constantly taking information in. And that processor, it's not AI, right? It's not, you have an incredible computer, an ability to think and an ability to adapt. These don't adapt. They just do exactly what the engineer programmed. So if it's this condition, engineer programs it to do this output. It's all got to follow the programming. How'd the programming get there? Well, when the vehicle's made, they upload a program to the computer, to the ECU. And some of you have done ECU updates. We reprogram those to, update logic. Maybe sometimes they realize, hey, you know what? Under this situation, we made the wrong call. Maybe if it's 20, 20, 20, and 0, we shouldn't have it completely reduce the brake pressure. We should only have it reduce a little bit. Well, maybe that would be better, but to update that logic, you have to actually reprogram it. So understand, they're just programmed information. That's basically a software update. So if you hear the software update's fixing something that they didn't have quite right or that they want to get a little better. Cool. So we continue. So we talked a little bit about the HCR modulator. I'll keep it a little bit simple. The power booster and master cylinders, that's the one that we did, like, let's say on that Prius or on the Lexus GX 470. That's when you have the whole unit, master cylinder, booster, the module, everything all together. So they can be separate or they could be together, basically is what it's saying. And then another very important part of the equation is the wheel speed sensor. So yes, there's other inputs. We will cover those, but the wheel speed sensor is a really major input. That wheel speed sensor could look like this. They could look quite a few different designs, and it's going to read off something that's spinning. So this example is a tone wheel that's pressed onto a CV axle. That's how it finds the vehicle wheel speed, right? So there could be slightly different designs, which we will cover, but that's what's going to send the EBCM the signal, or skid control. It's going to send the computer the signal. Here's what that looks like. So here's your system diagram. We're looking at the skid control ECU. We're looking at speed sensor 4. So that's all 4 wheels. That's an input. And what's up with the stoplight? That's an input. And within its own assembly, we're actually looking at the master cylinder pressure sensor as an input as well. However, the outputs would be solenoid relays, a solenoid relay valve, which there's 8, because we may have isolation and dump valves. We may have, these can vary in design, but overall we have to have a way to decrease the pressure or to isolate and hold the pressure. And then additionally, the skid control ECU controls the motor relay, which gives the voltage to the pump motor. So this is a slightly later system. This is a system where if we run the relay, the motor will run and it will pressurize the brake fluid, which will be read by the pressure sensor. This is a type of system that can actually apply the brakes with or without the driver pressing the pedal. We know that because it has a motor relay and a pump. That's why we have those. This may not even need a brake booster. It may or may not, but if it has a strong pump and motor when it was designed, we may say, we don't really need the brake booster. If we want more brake assist, we'll just run the motor longer and we'll store it in an accumulator. Something we talked about in hydraulics. And then I want you to notice these were inputs, right? And these were outputs. This one is kind of both. So the double line, that's CAN communication. So this module is on the communication network. It has to communicate with other things like the main body ECU, the combination meter. For example, if we have speed sensors coming in, we can either send a signal directly to the combo meter for what the wheel speed is. And we did on this older version, but since then we've actually eliminated this. It doesn't have an output to the speedometer. it actually just broadcasts the speed on the CAN network to any computer that finds it relevant. So anything like here, you can consider that bidirectional. It's not an input, it's not an output, it's communication, which can be both input and output, but we don't do it with like a voltage change. We do it with pulses. There's small electrical pulses that are basically, um, we'll do an on off, on off, on off, on off, and that will mean something. Exactly what it means, I'm gonna tell you, I don't know. If you got a little bit deeper into it, those certain pulses can indicate hexadecimal numbers. So maybe that letters and numbers. So maybe that on off was an H, and then on off on off was 2, and then you might end up with these long strings of hexadecimal code, and that hexadecimal code has a meaning. Luckily for us, we don't have to read code. If we want to know what's up, we connect to the DLC3. We connect the scan tool, TechStream, for example, and we can basically look at data. So if you want to know if the speed sensor is working, connect the scan tool and graph the speed sensor, and it'll give you the speeds. But just so you understand, technically, that's a sensor providing a voltage. This is processing the voltage, interpreting the voltage, converting it to pulses, converting to hexadecimal pulses, and then the DLC3 is interpreting that and then giving you a number. So the scan tool does a lot of work for us. Cool, kind of interesting. Then we can continue here some more of the components. So like, for example, we got the 4-wheel speed sensors. We got the brake actuator and skid control ECU, which in this Camry is out under the hood. We also have the engine control module, which is different from the brake control module. So the ECM is engine, and the skid control is really ABS. If there's codes for engine, those are P codes. If there's codes for ABS, those are C codes, chassis, powertrain and chassis, very different. These will communicate because we need them to work together. Some things the ECM will tell the skid control, and other things the skid control will tell the ECM. So they're both on the network. They're both communicating via CAN using that hexadecimal nonsense and whatnot. All right, but then also we got a stoplight switch that's mounted on the pedal. That's an input to the skid control ECU. We also have the instrument panel. That's going to tell us if there's a warning light. So like if we have a code, we're going to get a warning light on here. That warning light would have been requested by the skid control ECU. Kind of cool, makes sense. Now talking more about ABS, here's some of the principles. When we get into why ABS would activate or why it's even there, a lot of it has to do with why would the vehicle lock up in the first place. So I've had customers come in with ABS issues and they're very convinced that it's an ABS problem. Come to find out, it might just be the road surface, right? If it's a slippery road, it may be more prone to locking up, and it may actually activate ABS. You feel pulsation, you feel buzzing and stuff, right? They may come in and say, I don't know, something wrong with my brakes. I felt this thing, and then you might have to question them a little, like, what was the road like? Oh, I was in Big Bear and it was snowing. I'm like, well, it sounds like your ABS might have gone off. It'd be very normal for ABS to be activating on a snowy road. Is it possible? Did it seem like that? So, and the other thing, it could have to do with the type of tire, the condition of the tire, how much weight is on each tire. So if you have too much weight or not enough weight, they could both be locking up. If your tires are a little like me and a little short on tread, we may say, those may tend to lock up in the rain. So the weather's going to play a factor as well as the tires. And then the difference in speed, the difference between the vehicle speed and the speed of the tires. So like if you're, for example, let's say you are going kind of slow, like let's say maybe 10, and you apply the brakes, and all of a sudden you see that the right front tire drops to 5. that's actually noticed to go ahead and activate the ABS. So that would all be kind of normal. And then a fun fact for you, traction happens, maximum traction is about 10 to 20% of tire slip. So we do want the tires to lock up a little, but not to lock up solid. Just to maybe, if you ever hear an ABS stop that's really aggressive, you'll hear the tires kind of chirp, 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 chirp. Let's say you're watching like I don't know, some of these auto reviewers and they're testing the 100 to 0 stopping time. You may actually hear little chirps because they are locking the tires up a little bit, just not a lot of it. Right. So but however, traction falls off quickly above 20%. So if you lock the tires up a lot, that's when they liquefy the rubber and they just slide. So you want a little lock up, but not a lot. And then let's just say when we're normally driving, we do not want ABS lockup. So it's a tricky system because we don't want the ABS really interfering unless there's an issue. So if we're just stopping regularly, ABS needs to chill. I had some cars that ABS would activate on just a normal slow stop, and it would actually stop you from braking. Because remember, the ABS is gonna block off hydraulic pressure. So I'm pressing on the brakes, and the ABS is kind of fighting me, and no brake pressure is making it to the calipers, and the car's still going. And there was actually some recalls and stuff as a result of that. So basically, your ABS system is going to do like what I said. You need to pump the brakes to keep your maximum traction, but you don't. The ABS is going to do that. And the ABS is going to do it many times per second, much faster and much more effective than you could. And it's going to do it on a case by case basis for each wheel. So if you pump the brake pedal, you're pumping all four. But if your only problem is the right front, the ABS can pump the right front only, but keep the other three applied strong. So ABS is far superior to human driving. I didn't say it was fun, but remember, we're in the business of safety and consistency. So here's what that looks like. Your braking force is up, up, up. If we have a little bit of slip, we're going to let that go. If we have more than that amount of slip, we're going to cut it. We're going to engage ABS and we're going to cut that slip down, help it regain traction. Here's how we do so. Basically, let's visualize this. Pressure from the master cylinder. So let's say you stomp the brakes, you got a good booster, you make 600 psi. You're sending 600 psi to ultimately it should end up going down here to the wheel brake. However, it's got to go through these small passages and everything in that HCU, in that hydraulic control unit, or in the actuator, depending on what type of vehicle. Cool. So if there's no problems, that's what it does. It goes over, up, down, out. But if we have an issue, like let's say the ABS is locked up, what we'll do is we could actually open up the dump solenoid. And what'll happen is that pressure will come in, go over, go over, go over, go up, and then go, nah, never mind, right back to the reservoir. Boom. And just basically bleed it off. So the dump solenoid essentially bleeds off the brake pressure. So if your right front wheel is locked up, the wheel speed sensor says so. The skid control ECU sends a signal to the dump valve for the right front tire and says, hey, bleed that off, bleed it off, bleed it off, bleed it off. And when it bleeds off, it's going to verify it bled off by seeing the wheel speed sensor jump back up to the 20 miles an hour in our example. Right. So, and then isolation can actually stop you from applying more. Or what's really interesting, it could actually hold it applied in the case that we're using one of the more advanced features like track or, hill start assist or something. They can do some cool stuff. And then the other thing to consider, we got an accumulator here. The accumulator's job is to hold pressure for as needed. Now, yes, we have a pump and the pump could make the pressure, but that could take a little bit of time. So we constantly keep pressurized fluid in the accumulator so that we're ready at any moment. Boom, we got pressurized fluid. We could send it to any wheel instantly. Cool. So it's kind of fun. And this just kind of explains the cycle and how fast it can do it. Potentially up to 16 times per second. Much faster than you can pump the pedal. You can't compete with that, I can assure you. And also, sometimes when we're doing these ABS activations, it can feel like a pulsation and a vibration, and the customer may say, "Oh yeah, I have a pulse." That's not a pulsation. That could be totally normal. It could be normal, and they are supposed to move around a lot. Here's an example. Master cylinder could be non-integral. There's your master. That means the ABS is going to be somewhere down here, like that picture we saw before. Now, if it's integral, that means it's the master cylinder and the ABS, which is kind of nice, but kind of not nice. If we have a bad master cylinder, we now need to replace the whole assembly, including the ABS. Or if we had a problem with the ABS unit, we're now also replacing the master cylinder. So, for better or for worse, they can be separate or together. And integral used to be on older cars, but that what we're calling the brake actuator, that's made a big comeback. Those are on everyday stuff now. Now that the master cylinder itself on these is the same. So how we diagnose it is the same. How we replace it is a little different, a little more expensive. And so that's why you can see this is your typical master cylinder. Now they may use slightly different. Some of them don't actually have the ports, like the compensating port, but as far as how we diagnose it, how we work with it's not really any different, right? And then we get a little heavy into the master cylinder, so I think it's more important. As you guys understand, the ABS control module can send commands to the HCU. So if the control module wants something to happen in the hydraulic, system, like let's say the HCU, let's say that the skid control ECU wants more brake pressure, it can send a command, hey, run the motor to increase the pressure. Or let's say that it sees a problem with wheel lockup, it will send a command to one of the solenoid valves. And remember, the solenoids control the valves. So no, it's not really rocket science, I don't think. And then, yeah, we'll go ahead. So let's say what we were talking about, we'll back up just a bit. Wheel locks up. The wheel speed sensor shows it. The wheel speed sensor sends a signal to the skid control ECU. The skid control ECU sends a command to the solenoid valve. And like, for example, it can actually close the solenoid valve, which is isolating the brake circuit. That means as you continue to press the pedal, it's isolated, so it's not increasing. So that's an isolation valve. But let's just say it continues to lock up. That's when it actually may signal the dump valve. So the isolation valve just stops it from increasing further. The dump valve will actually decrease it. And it's going to monitor that through the wheel speed sensor and make adjustments, like I said, up to 16 seconds, 16 times per second, very rapidly. So that's kind of the overall. There's several designs. They did have single, 2-channel. Those were very old. For a while, they had 3-channel. 3-channel was interesting. It had a left front brake, a right front brake, and then it had a rear brake. It could basically control both of the rear wheels together. It couldn't control them separately. So it was 3-channel, kind of old. And then we went to the 4-channel quite a few years ago, and we've never looked back. We're now monitoring each wheel and controlling each wheel independently. So in the event you do see, like on the ASE, something about a 3-channel, that was the thing. I don't know if anybody's doing it now, but quite a few were doing it pretty recently. 4-channel is going to have 4 sensors. 3-channel is going to most likely have 3. Front, and then also there might be one in like a rear axle here, like in the diff, possibly for that 3-channel. Pretty common for those. Or it might even use the vehicle speed sensor. And then we've evolved and improved, and we're a lot of times using more simple methods now. So we used to have isolation and dump valves, and now instead, what we'll do is we'll actually have uh, a single valve that can be in three different positions. So we have one solenoid that can make the valve isolate or the valve dump. So it went from big to a lot smaller. So we're more than likely going to be sticking with the single three position solenoid valve. So at that point, you just need left front, left rear, right rear. And they can isolate and they can dump. So they only really need four. Kind of better. So those can apply, hold, and release. Actually, slightly different than isolate and dump. Isolate is hold, dump is release. Different terms, same thing. But on the newer systems, especially when we get into some of the more advanced ADAS systems, like collision avoidance, they can also apply the brakes. They don't need you. Like I was saying, they can run the pump. They've already got the fluid stored in the accumulator. They can open the apply valve and apply the brakes for you. Your foot never touched the brakes. They don't really need you. So here's kind of what that looks like. We got this accumulator storing the pressure. We got the pump. As the pump motor runs, it pumps a piston that builds up the pressure. And that pressure is going to be either A, replacing the master cylinder pressure, or B, helping the master cylinder pressure. So if you're pushing on the master cylinder, you're still working it, but the pump can help you a lot. Or if you're sleeping and you're about to rear end a car, you don't make any pressure on the master cylinder. The pump just does it using the accumulator. Pump will do it anyway. It don't need you that much. It can do some other things. And then additionally, as you can see, this is a solenoid, which is electrical. It's a winding. So that solenoid, because it's an electromagnet, can pull the valve up or push the valve down. So if we wanted to dump the pressure, for example, we would actually activate the solenoid, it would pull it up, and that would reduce the pressure, go to the accumulator and go into the pump. Right. So that's basically the multiple position. This is a three position. It can do both all of those. It can apply itself, it can isolate it, and it can dump it. Or like these are two positions. These are a little more simple. This can be isolation and dump separate. So kind of fun. These are basically on off and on and off. Cool. And then and this gets into a little bit more of the types of systems. So basically one system has low pressure and the other system has high pressure accumulator. It's not real critical for you to know, but just know that in the high pressure system, it has a little bit more safety. And so if you're following service information, it's going to say, hey, you need to do, for example, 40 pedal pumps to depreciate, to decrease it, because it could be up to 2,700 PSI. So that's enough pressure to cause damage. I'm not sure that's enough pressure to cut your finger off, but it might be. But it's definitely enough pressure to cause some problems. Right. And so here's an example of that system. This is a slightly different design, but we've got the pump driven in the center. That's going to pump the pistons. That's going to build the pressure. And then we've got a total of 8 valves. And each of those is going to be one channel. So if this is your left front, actually, this is your left side right here. No, I'm sorry. That is left rear. Bottom left is your left hand front brake. Isolation valve and dump valve. We wouldn't likely operate them at the same time, but that's why we have 8 valves. It's an isolation and dump per wheel. And this kind of shows a little bit more of the versions of what it's doing. Remember, we're just moving this valve. That's all we're going to do. Now, do you think it's possible? Because we're looking at these valves, we're looking at all these valves. I mean, this gets in here. These valves all have to be in a certain position to have it do something. So like, for example, right here, this is with track not active. This is just a normal stop or a normal go. And then like, if we're trying to increase traction, we can actually move these valves. You see, we actually change their position, and that's going to apply pressure to one of the wheels, let's say the right front wheel, which is going to send more power to the left front wheel, we need these valves to move exactly where they're supposed to move on the spot. But if you notice, there's quite a few valves in there. You think it might be possible for one of those valves to stick? In which, what might have caused that? So this is when this came out, a lot of people were really concerned. You need to flush the brakes. You need to be really careful with these. But I'm going to tell you, sticking hydraulic, sticking ABS valves, it's not something I hear about at all. They've been very reliable. So for that reason, basically, they've been extremely reliable. I think it's just a good overall for you to know. Yes, there are, 8 to 12 valves. They all need to be freed up. They all need to work correctly. All those valves are controlled by solenoids. And you know what? They work pretty good. So I don't think we need to spend a ton of time on on the intricate details of how they apply, dump, release, hold, overall, just know that's what's happening in that HCU, in that actuator, we may say. Right. So going further, let's talk about the wheel speed sensors. This is something that you need to know a little bit more. Wheel speed sensors have some issues. So like low speed, for example, would look like this: moderate speed and high speed. You can't, I did a whole video on this and I'm gonna assign that one, but you can diagnose these in several different ways. The number one way is graphing. So graphing on an oscilloscope, this is going to give you a full view of exactly what's happening. Whereas measuring with a meter, that's going to tell you if it's making voltage or not, but it's not really telling you how the voltage is changing. This gives you a lot of information. So real quickly, we might need to jump into oscilloscopes when we're diagnosing some of these wheel speed sensor issues. And that's something you will do. I'll bet you $1. But the different types, we may have a passive. So the passive was that sine wave style. Those we just basically generate AC current by spinning a piece of metal near a magnet. Simple. Each high and low is a tooth and a not a tooth. Then we have active. Now, active, we need to actually power those. So the passive is, not real good up until 3 or maybe even 5 miles an hour. The active, those are going to be accurate as soon as you start moving. And we do some pretty cool stuff with those. But just know passive and active are different. The active is going to be digital. It's going to be more precise. So here's an example. This is a variable reluctance. This one's a 2-wire. It makes an AC sine wave, and it's just basically using the magnetic sensor, which is having current induced by the teeth passing by. And as the tooth gets right in the center, that makes a high point. And as it gets further away, that makes a low point. And then the next one starts to come in. So it starts ramping up. It's at its peak. It's ramping down. It's back up. It's at its peak. It's ramping down. It's back up. It's at its peak, right? It's going to do that over and over. If we had damage on one of these teeth, it might actually be a little tricky to diagnose. It might take the oscilloscope. All right. And so that's one type. Magnetoresistive, but as we get more into the Hall effect, those are where we start to get into some more of the DC. So this is a Hall effect. The Hall effect needs to be powered. That's going to power the chip, Hall effect chip. And then we're going to ground. And then we're also going to have a signal circuit. So this is going to make a square wave, right? Like it's going to go positive, 0, positive, 0, positive, 0. Each high is due to a tooth. Each low is due to not a tooth. So in that way, they're almost the same. The main difference is you just have to know these are going to be accurate as soon as you start moving. And if you go to do more diagnosis, you're going to have the meter set to DC on here. Whereas back here, you're going to have the meter set to AC. And then here, if you picoscope it, if you do an oscilloscope reading, you're just going to have different settings. You're going to have it on DC. You're going to have different voltage, different, different frequency, and you're gonna set it up per the manufacturer recommendation or compared to a bank. So like Picoscope has all the sample waveforms. You can pull a sample waveform, get the numbers off it, and then most likely that'll be exactly how you want to see this image. But this image is going to tell you the whole story. So if we had a broken tooth, that would be hard to diagnose. But if you did the Picoscope or an oscilloscope, you would actually be able to literally see the broken tooth um, on the waveform. So it'd go from like this impossible diagnosis you can't figure out to, oh, it's got a broken tooth, and then you're good. So like, for example, here's an example of a slow Hall effect, and here's an example of a high Hall effect. It can vary, just like the ASE type sensors on speed. And so now here's another cool thing that we've done that's really good. We need to know which direction it's traveling. So what we do in forward is different than what we do in reverse. So how do we know which way we're going? Well, on those types of sensors, if we're going in forward, that's going to do south pole. Actually, if we're going in forward, that is going to do North Pole, then South Pole. North Pole, then South Pole. If we're going in reverse, it's going to do South Pole, then North Pole. South Pole, then North Pole. So it's kind of interesting. We can use the active sensors to also tell which direction we're going. You can't do that on a passive sensor. The passive sensor is not even accurate till 3 or 5, but it also has no idea which direction you're going. So if it were me, I would focus more on this type of style right here, because that's what's on all the modern cars. These are simple and they're fun and they're cool, but they're not doing this anymore because there's some major limitations. So learn this by all means, but I'd say master this because this is what you're going to be seeing. All right, so kind of fun. Um, and there's some things to really complement that on the other video that I made. Now, as for the brake switch, some people have had some questions on this because you took electrical, so you know a little about it. But the brake switch, first off, let's say it activates the brake lights. Cool. That's simple. That's easy. But it's way more than that now. Remember, it's an electrical input to the EBCM. That EBCM needs to know, are you pressing the brakes? Because if you're pressing the brakes and we're seeing difference in wheel speeds, that means they're locked up. But if you're not pressing the brakes and you're pressing the gas pedal and we're seeing unequal wheel speeds, that means we're spinning the tires and we need to do more like traction control. So it's an important input. A brake light switch is on off. It's either applied or it's not applied. But if it's a brake pedal sensor, that can actually tell us if it's like lightly applied or if it's lower to the floor. That can actually measure the position of the brake pedal. That can give us more information. As far as it goes to the system, it's kind of the same, but we test a brake light switch on or off. We test a sensor sweeping and voltage, and we probably used the scan tool before we got the meter out. So here's an example of that brake light switch. This brake light switch with the pedal released, the pedal pushes the switch closed, or it pushes the switch open. And when it's open, it doesn't light up the brake lights. But if we have our adjustment off or we apply the pedal, see the pedal's going to pull away, the switch is going to actually come to the left and you can see the contacts. Those are closed now. Closed means light the light, right? Basically, 12 volts comes in, goes to this contact right here, but there's a gap right there, so it's not connected. So it's done. When we step on the brake pedal or our adjustments messed up, that's kind of my point. We did quite a bit of master cylinder work and we had some brake lights staying on, if you don't remember. 12 volts comes in, it goes to this contactor. This contactor is actually touching this contactor, so it passes through, and then it sends the 12 volts to the light bulb, the rear lights, brake lights, and lights them up. That's all a brake light switch does. It's so simple. You can see right here, this is threaded. A lot of times it's threaded, or they can vary in designs. Like this one, for example, looks like it's held in by plastic. So sometimes there's an adjustment that's threaded, or it might be like a plastic where you have to do a little turn and set it and then lock it in. And this one's actually the sensor, like I was saying. So a more modern system is most likely going to use a brake pedal position sensor, because it's not going to tell it's on and off. It's going to tell like, oh, this customer slammed the brake pedal to the floor. We mean business. That's going to give it a more precise view of what the driver's intentions are, rather than just on or off. See what I'm saying? So it's not super complicated. And then basically we talked about the EBCM. It does have circuitry to process signals. So like those wheel speed sensors, right? They could be AC or they could be DC. If they're AC sensors, it needs to have hardware to be able to take that AC voltage and current and basically convert it into a signal for the ECM, for the control module. Or it could be DC, right? So it's got some hardware there. It's also got a electronic data processor, so computer memory. And then it's got drivers, and the purpose of the drivers is to basically send voltage or ground, provide voltage or ground, or not provide it. You know, sometimes we're going to get into like duty cycle. It might give pulses. So that's all part of the EBCM. And then, of course, like I said, it's programmed. It's programmed by an engineer who, you know, says, hey, if you see this, this, and this, do this. If on your input signal you see X, Y, and Z, use the processing power combined with my memory, which is the program, and then control the outputs to do action, to do the solenoid, to isolate or dump, etc. Right? So that's the picture. This was a pretty cool one that's a little more advanced. This one has, I'll run through some of the inputs right now. Left front, left rear, right rear wheel speed sensors, and those are the Hall effect DC type. It's also got an ESC switch. That's an interesting one. Let's come back to that one. It's also got a brake pressure sensor. I like that because that actually tells me what the brake pressure is. But in addition, it's got a brake light switch. I know I skipped one on purpose. And something a little more complex, or something pretty simple, parking brake switch, but something a little more complex. It's got a rotation rate sensor. So that's going to get into yaw, YAW, yaw sensor is going to tell us what the directional and what the actual direction of the vehicle is. So when we get in the more advanced systems, we not only need to know the wheel speed, we also need to know, is this car spinning? Because if it's spinning, we might do something slightly different, right? And then all those are going into the electronic stability control system. That computer is looking at all of its programming, and it's going to send signal to the solenoid valves, which are going to modify the pressure. It may also do some things like run the pump to build pressure or slow pressure down. It may also, if there's an error, think about it. It may actually illuminate the lamp on the cluster saying, hey, there's an error. If there's a code set, it's going to illuminate the ABS lamp or service, ABS message. Same with ESC. Now the ESC switch, why would we turn an ESC switch on and off? Well, we can't turn ABS off. There's no way to turn off ABS unless you set a code. So if you want ABS off, set a code. Your ABS will be off. But they don't want the customer to be able to disable ABS. You can't disable ABS the customer. You can, however, disable some traction control and possibly even electronic stability control. So that would be ESC off. You push that button, it's off, disabled. It's kind of interesting. And then you can see it shoots it out on the CAN network, and a number of modules are on that network, including the instrument cluster. So they all get the information they need from the EBCM, or the skid control ECU, because they're on the network together. And then also we can do diagnosis. This is where we would connect, but most of the time we're actually going to connect onto the network, and then we're going to work to on the module through the CAN network using the scan tool. It's kind of fun. Here's a couple of details. EBCM is going to perform some sort of a check. A lot of times it'll illuminate the ABS light for a moment and then turn it off, just to make sure the bulb works. Sometimes I've seen ABS units actually run a little bit and click and make some noise. Like when you first get rolling, especially on the older ones, there'll be a little ABS thing going on. That's normal. If That's normal if all the other ones do it. So if it's a Corolla and every Corolla does it, that's fine. That's normal. Now, if it's older, they would actually blink flash codes. So Toyota was really interesting in this. They're like a 2002 Tacoma, the skid control ECU was not on the network. You couldn't communicate with the skid control ECU through the tech stream. You couldn't get live data. You couldn't do active tests, nothing. All you could do was short two terminals and it would make the ABS light flash in a pattern. Long flash, one, long flash, two, short flash, 1, 2, 3, 4, 5, 6. That would be a 2, 6, code 26. And that was just because, that ABS unit would do self-diagnosis, but they didn't bother to have it communicate via the CAN network at that time. It wasn't something you could do much with. So it's possible you might run into some of those. But generally speaking, our main workhorse is going to be the scan tool. Scan tool does a lot of stuff. Scan tool is going to help us diagnose it. We could do a number of different things. This talks about, the diagnosis. Basically, you have to understand how it works. You have to have access to service info. You have to be able to check DTCs and refer to the troubleshooting instructions for the DTCs. And it's going to be basically like how we diagnose DTCs for anything else, following a process, not real complex. And so not real different than a lot of the other things, but basically the EBCM is going to make some decisions depending on the sensor information, the software program. And then that's going to not only be sent, especially on the later style, to control the valves, but look at this. This is new. On the later system, it's going to actually send information to the vehicle powertrain control module, so the engine control module. Now, let's go back to that GTO. Remember, that GTO, he started with burnout. It saw the two rear tires start to come up in speed. And then it said, oh no, I'm not supposed to do that. It not only applied the brakes, it sent a signal to the engine control module and said, hey, cut the fuel on that, cut the fuel. So he tried to punch it and it went, bleh. Remember how I said it went, bleh? That's because it cut the fuel. It turned the injectors off. It made no power and it bumbled and grumbled and bleh, 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 and then it kind of took off. So in the later system, we're also going to use that information for other, especially powertrain, which could be engine or transmission. It can even cause an upshift and it can affect the timing, which is going to pull power as well. So, some good info. A lot of this stuff is going to be, kind of outdated, but back in the day, we used to actually have a little key. It was a jumper. I believe it or not, I actually have one, but it'd take me too long to find it. We would actually insert that into the DLC and that would flash the codes. That's a code retriever key. And then scan tool is going to be more normal. And then if we need to get a little more advanced, we do the oscilloscope. I put that on another video. So here's those tools. Scan tool is going to be really good. We may use an oscilloscope, and our meter is always the meter can do a lot. The meter just can't do everything an oscilloscope could do. And my go-to would actually just be the scan tool, because the scan tool can show me data. And if I see a problem with the data, then I might go to the oscilloscope, or if it's inconclusive, I might go to the oscilloscope, but I wouldn't go to the oscilloscope first. All right, and so that's kind of some of the tools. Now let's discuss modifications, because you gotta be able to figure out the customer's car. And sometimes it's their fault. So when this system's designed, all this stuff, they're looking at the weight, the speed, the tire size, the brakes condition, the brake pads, all that type of stuff. Center of gravity, all that stuff. That's all factored in the engineer's programming that he uploads, right? So or she, they, them. The engineer, they, them uploaded some sort of a software based on all this information. And then the customer does a bunch of modifications. So now the software may or may not function exactly the way it's supposed to. See where I'm going with this? So, like for example, you go ahead and you lower or raise the vehicle. That's going to change how the vehicle handles. It's possible a problem could be caused by a modification, but that does not mean that, oh, a vehicle comes in, it's modified, it's no longer warranty. So I want to make that very clear. You just have to understand there is a relationship between this ABS, this VSC, stability control. All this is tied into how the vehicle was made, and if it's been modified, it may have an effect. You have to use your brain and on a case by case basis consider that, right? And so same with like braking, it can affect the braking, it can affect the handling, it can affect a lot of that type of stuff. And so what would be really cool is if we could get a tuner to program that EBCM for the modifications, but generally, I don't really see that. And same with like if you change the gear ratio in your transmission and your differential and your transaxle, that can have an effect on these systems. They, they have an expectation and they have a prediction for how it's going to function, which could be changed. So just be aware. All these things could change how the vehicle handles. Okay. Now, if we're going to diagnose, this is more realistic. You're probably not going to get a customer who comes in and says, "Yeah, my ABS functions slightly different than new." Like that's not likely. More than likely, because the system is doing OBD, onboard diagnostics, it's checking itself. It's checking today, it's checking tomorrow, it's checking. You start moving with the vehicle, if three sensors start increasing miles per hour, wheel speed sensors go 1, 2, 3, 4, 5, and one of the sensors goes 0, 0, 0, 0, that sounds like it could be a lockup, right? But then the system references the brake switch and says they're not pressing the brake pedal, so it can't be a lockup. And then that 0 continues for like the next several seconds. The other speeds are going up and down, and one of the speeds is still 0. Yeah, that doesn't make sense. That tells me probably there's a fault with that sensor and or the reluctor wheel or something. So it's going to set a code. So you're going to get a vehicle, it's going to have a code. You'd be like, oh, okay. Customer states the ABS light is illuminated. And you're going to do a visual and check codes, and you're going to see left front wheel speed sensor circuit open. And that's really what you're going to troubleshoot, right? So a lot of what we do is diagnostic trouble code related, DTC related. So be ready for that. Not a real big thing. Like it says, mostly going to be DTCs, store them in memory, check for DTCs. And then this kind of runs you through like some of the steps. So if you connect the scan tool, navigate to code retrieval. If you do pull a DTC, see if there's any technical service bulletins, follow the diagnostic chart. Once you correct it, clear it and road test it, right? It's not really rocket science. That's what we're going to be doing tomorrow, right? And now servicing it though, it could be a little different. So every car you worked on had ABS. Old cars didn't. Bleeding was a little more simple. If you're going to bleed a car with ABS, which they all have, by the way, you may need to follow some specific processes. Like, so for example, if you get air in the ABS unit where those valves are, it can be very difficult to get it out. And that's why, like, for example, a lot of times it'll require a scan tool. Some EBC, electronic brake control systems require a detailed step-by-step process. Sound familiar? So we were a little ahead when we were doing those actuators and stuff, but it makes sense. And then like what this is saying, don't let air get in the EBC system because it can be really tough to get out. I totally second that. So pretty good. And then this is just going to say like, here's the bleeding. Research the specific procedure. That's why I thought about cutting this and then I left it. You need to research the specific procedure. You don't do what I'm about to tell you, but this is a sample. a lot of what you've done. Maybe connect the pressure bleeder adapter, connect the hoses to drain, to get the at the bleeder for the air. Click bleed brakes, and that's going to do an active test. Pressurize the bleeder, pressurize the pressure bleeder, open the valve, and then it's actually going to say, maybe like charge the battery, set the parking brake, and when you continue, it's going to actually actuate the valves. So the reason I left this was if you were bleeding, you knew you were supposed to follow the process, but you didn't know why. Now I'm trying to tell you why. Those valves have spots where air can get. And if you don't follow the process and that valve's in the wrong position, you're not going to get the air out. If you don't have the scan tool, you don't have a very good way of doing this job, to be quite honest with you. So that's the more technical reason why. And then when you're done, you're all finished off, check the brake fluid, make sure it feels good, make sure it doesn't set any codes. Now, as for if you're going to work on it, you may need to do a depressurization. Sometimes you, again, follow the service manual, but sometimes that can be a scan tool function. And other times it's something like turn the car off and pump the pedal 40 times. Could be one or the other, right? As these are kind of saying, could be multiple different ways to do this. Like the Prius, for example, disconnect the brake level sensor, the brake fluid level sensor, so that it won't run the pump to repressurize it, because that's some of the problem with some of the more advanced systems like hybrid. You'll depressurize it, and then the car will power itself on and repressurize it. So follow the process. Not a real big deal. And this is talking about repressurize, following the steps, pulling the fuse, potentially pumping, pumping, pumping. And that, and you'd really mainly do this if you're going to do service, like if you're going to take the system out, undo the system, something like that. Not a real big deal. And so again, I can't stress enough. Follow the specific procedures and make sure it's been depressurized before you get too far. Okay, not a big deal. Now, wheel speed sensors. Most of the time you're diagnosing a wheel speed sensor, you're probably going to get a DTC right there. Here's something stupid. I had one. I was troubleshooting it. I had a wheel speed sensor performance code, not an open circuit, but a performance code. And I kept going and checking the sensor and checking the sensor and rechecking the sensor. I put my little meter and I did all this stuff. And then I talked to the more experienced technician. You know what he said? Did you check the tires? Like, yeah, what about them? They're all the same? And I'm like, no, I don't know. Yeah, they should be. I said, well, I know they should be, but I didn't ask you, should they be? Let me go look. Customer had the wrong size tire on the car. Think about that. If you got 3 big tires and 1 slightly smaller tire, the slightly smaller tire is going to spin a little faster. Well, the system looks for things like that. It says, wait a minute. Hold on a minute. Something right. I got 30, 30, 30, and 32 miles an hour. That sensor is not accurate. It can set a code for that. And it may not be the sensor at all. It may be a different size tire. Don't ask me how I know, I just told you. I was an idiot. I chased that car around trying to fix it. Never thought to check the tire size. So this was a good point. Back out, take a look at it, an overall look. And then, additionally, a low tire, if it's a tire that's actually run really low, that could actually cause ABS issue too. It's true. And then when we're really trying to get into more advanced diagnosis, that's when we'll bust out the oscilloscope. We may call it a DSO, digital storage oscilloscope. We could even use a graphing multimeter, but if you're going to go to that, you might as well use the oscilloscope. And the sensors depend on which time. They could be an AC sine wave. They could be a digital square wave. You need to know the type. Understand? And now get into the more advanced systems. This is Toyota, for example, has all these other systems. We've got the same inputs, but we might add some. We might even have sensors from other systems that are talking to the ECM. And the ECM is multiplex is a term, right? Multiplex is sending it out on the network, and the skid control ECU is interpreting that info. So now let's say they may look at wheel speed, stoplight, yaw and deceleration sensor, steering angle, fluid level, accumulator pressure, master cylinder pressure, the DAC switch, downhill assist control, the auto LSD switch, park neutral, rear diff lock, low four, ADD, which is automatic disconnecting differential, parking brake switch, and battery. There's a lot of inputs to a very advanced system. The skid control ECU processes, and it can control even more things. Control solenoid valves, switching solenoid valves, brake system warning light, pump motor relay, VSC warning buzzer, stoplight control relay, solenoid valve relay, and pump motor relay. So we'll just pick one. Most of these we've covered. How about A-track? Actually, better yet, auto LSD. Auto LSD and A-track are kind of similar. An auto LSD is where you get stuck in the snow and your right rear tire is spinning like crazy because it's further off the road, and your left rear tire, it's on dry pavement. But the problem is all the torque is transferred to the easiest side, right? The path of least resistance. Torque is kind of like water. It takes the path of least resistance, and people are kind of like water too. Whatever is easier. You know what I'm saying? So anyway, your right rear tire spinning like crazy, your left rear tire just sitting there being chilling. And then what the automatic limited slip differential will do, like we talked about a little bit, it'll notice those wheel speed sensors. It'll communicate that skid control ECU. The skid control ECU, so you know what? Let's pump the motor up. Let's activate the right rear apply valve, and let's apply brake pressure. You didn't even have to step on the pedal. The pump can do that. It applies brake pressure to the right rear, slows it down, which, oh yeah, sends torque to the left rear, and then boom, you're unstuck, right? So this whole auto LSD has nothing at all to do with the differential or a locker or four-wheel drive or power. This is all a version of electronic braking. It's not really ABS. It's not really traction control. It's not really vehicle stability control. It's an other system that uses the same skid control ECU and the same inputs plus some new ones. Cool. And same with crawl mode or hill start assist is a really cool one. Hill start assist with a manual. You come up to a steep hill, you push the clutch pedal down. A lot of times, if you push the brake pedal kind of hard, it'll hold. That'll actually activate the isolation valves. You'll build the pressure. It'll activate the isolation valves. You'll take your foot off the brake, but the isolation valves will hold the pressure. So therefore, you can get your foot over to the gas pedal. You got your foot on the clutch and your foot on the gas. You ain't got no foot on the brake. You don't need no foot on the brake. It's got like a hill start assist. And then the second you let the clutch pedal up and it starts to see a little bit of movement, it'll release the isolation valves, dump them, and boom, you're moving. Now in the ghetto, that's what we used to do with kind of the ghetto, not the ghetto, but the country ghetto. You know what I'm saying? When you're broke boy, you gotta learn to use the parking brake. So if you're kind of janky ghetto, you might use the parking brake to get started. So that way you don't roll back that much. And you might be pretty quick where you don't really have to use it at all. But once in a while, you get somebody that'll pull right to your bumper. You're like, man, when I get ready to let off the brake and try to get the clutch out, I'm afraid I'm going to roll back 6 inches and hit them. Well, you use the parking brake or you can have hill start assist. The technology, we do have the technology. And then we get into this, any one of these all use the same system. And there's more. So with electronic brake force distribution, we talked about, we no longer need that metering valve, proportioning valve. We got all we need right here. We can actually use those valves, that the isolation dump valves, to modify the pressure as needed. We don't need to limit pressure to the rear wheels using a proportioning valve. We'll just limit it using the dump valves. And that way it's kind of customizable. right? If we have a whole bunch of weight in the back of the car, we may no longer want to limit it as much, and we can custom adjust on the fly based on our inputs, based on our wheel speed sensors, right? So it's pretty neat. Um, like brake assist, that's where it'll actually increase. It could increase and apply more brake pressure to stop faster. When you look into that hydraulic circuit, remember we got the brake pedal, and the brake pedal can make the pressure, but so can the pump and motor. We can increase, we can reduce, we can do all sorts of stuff, right? Pretty cool. And then like here's track. So when we were talking about track can actually um, help with, it could be a number of different things, but let's say that you're accelerating and you have, like in this case, your right front tire slipping. Under load, it can actually apply the brakes to the right front tire to get the torque to left front tire. So track is kind of like that auto LSD. It's just more for cars. Nobody's got like, oh, I've got a Camry with the automatic locking differential, like, but they're similar. And VSC again, that's going to have to do with using the steering angle sensor, using the yaw sensor. You know, the steering angle sensor is going to tell you where the vehicle wants to go, and the yaw sensor is telling you a little bit more about like where is the vehicle going. It could be understeer, it could be oversteer, right? So those are all related to VSC, vehicle stability control. And so with VSC as well, VSC is essentially ABS plus traction control. Traction control is what we talked about when that GTO stumbled and blah, 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 right? But we add the directional intent, right? So we know if the customer is trying to turn and it's understeering, or like in this case, let's say it was rear wheel drive, the customer is trying to turn and it's actually oversteering, which means the rear wheels are probably slipping, by the way. If the rear wheels are slipping, we may actually want to cut engine power. So that's more what this is saying. If your skid level's high, it's going to cut your engine power and it's going to increase your brake pressure. So it's going to pull the power and apply the brakes. That's going to help you stay under control. Cool. So that's what stability control is. All right. And then this talks a little about the yaw rate sensor. So the yaw rate sensor needs to always be mounted somewhere near the center of the car. It's probably under the console, probably under the center console. It's where it's going to be. That's going to tell us rotation on the Z axis. So that would be like this. That's going to tell us if it's sliding on the X axis, that's left to right, or if it's accelerating or decelerating on the Y axis. It's going to tell us all those. This is pretty complex sensor. It's basically multiple sensors in one sensor, and they can be expensive. And I haven't had a ton of problem with these. The only few problems I've had is because they're kind of low. I did have a car that got flooded. Like this one has a sunroof, right? And I showed you guys the sunroof drains last week. If this car gets wet, that yaw rate sensor, it's pretty easy to get those underwater if it's got a lot of water in it or if the sunroof leaks or something. And I've also had them one where it actually wasn't bolted down tightly. It was loose and it was vibrating. So like you see right here how it says impact tools and vibration may cause damage. Well, this one was loose and the vibration was causing damage, and it needed to be replaced and the new one tightened. It's kind of interesting, but that's the sensor all in one. And that's going to do the deceleration, acceleration. That's going to do the yaw rate. So these magnetic forks, they'll actually change as it rotates because north and south pole are always current, so it'll actually flex a bit. And then and that's really mainly two. It'll just use two of these acceleration deceleration sensors. So the car's accelerating or decelerating, that's front to back. But if it's side to side, that's acceleration deceleration too. It's kind of interesting. But exactly how they do it with the beam and the mass, I got to tell you, on this piezoelectric element, don't know the details. The image that always made sense to me was picture a bowl. You have a bowl, you drop a BB in the center. You put it in the car. If you're not moving, the BB's in the center. If you accelerate, the BB is going to go to the rear. If you decel, the BB is going to roll to the front. If you turn left hard, the BB is going to roll to the right. If you turn left hard, the BB is going to roll to the left. So to me, I've always visualized that, and I've always known the sensor basically knows what direction the BB is going and how far it's going. To be honest, that's not how the sensor actually works, but for you, it's actually perfect, and that's how I understand it too. I don't like to make things really complex. So I visualize the BB, so if I were to pull up on live data, the yaw rate sensor and look at acceleration and deceleration, I should be able to see the response I expect based on what I'm doing. I'm braking, I'm accelerating, right? So that's how I get a good idea. Most of the time, a problem with this is going to set a DTC. You're really just going to be continuing with DTC diagnosis. And then another one, the steering angle sensor. Want to make a quick point on this. The steering angle sensor is going to be in the steering column, and it's very critical that it's what we call zero, the 0 point calibration. When the car's dead straight, this should be reading dead straight. If a car comes in with a crooked steering wheel and we go ahead and we do an alignment, and now we move the steering wheel from here to here, your steering angle may say that you're steering right. So after we're done with an alignment, we actually need to re-zero this. That's kind of something for the second half of the class, but because it's in ABS and VSC, you have to know this is an input and it's an input to the system. And if we do a change, we may have to actually calibrate it. Alrighty, and that's kind of what this one's saying. So Toyota likes to call this vehicle dynamics integrated control, VDIM. They're going to use ABS, track, electronic brake distribution, and VSC all combined, and that's VDIM. Right, but it gets further than that. We talked about these systems already: A-Track, Auto LSD, downhill assist, hill start, multi-terrain ABS. So we'll have ABS for the street and we'll have ABS for off-road. They're a little different. And crawl control, which we do have a couple vehicles with that. If you were to get stuck, you could put it in crawl mode, and literally you'll take your foot off the brakes and the gas. It'll use the engine to turn the transmission, and it'll pulse the ABS, and it'll basically spin the wheels kind of like this. And it'll help crawl its way out of, let's say, sand. It's basically powering all four wheels in a four-wheel drive, but using the ABS to lock up and unlock in a weird pattern that'll actually help get it unstuck. So it's a pretty neat system. We'll play with that next semester. Cool. So there's A-Track explained, like we were talking about. With A-Track, we're able to send the torque to the correct wheel. Without A-Track, we're not. The LSD you can see it's kind of the same, but this is a truck and it's on the rear wheel, so that's why we'd call it an LSD. Downhill assist we kind of talked about. That'll if you're going down a hill off-roading, like if anybody goes off-roading and you got a big old hill, you might have to ride the brakes for the next half hour. Those brakes they're going to be struggling a little bit, and it's going to be tough because you're going to be locking them up and then unlocking them. So downhill assist will use ABS as needed to only slow down the correct ones and keep you under control without locking up. So it's kind of neat. And then hill start assist we talked about with the clutch, right? So we're pretty good there. It also works for automatics, by the way. So if you come up to a light and it's kind of uphill, if you press the brake and hold it and then let go, it'll just hold it until you start to push the gas pedal and starts to move, and it'll release it. So what I said was with the clutch is true, but it's just mainly easier to explain on a manual. We still do it on the automatic, so you don't have to sit there at the light and hold the brake pedal the whole time. All right, we talked about the ABS, how it depends on if you're on road or off road, but you can put it in an off road mode and it'll change the way your ABS works. So it's pretty cool. You can put it on mud and sand, loose rocks, moguls, which would be like bumps, like whoops, or rock mode. And each one of those is going to basically refer to a different program the engineer put in, and it should fine tune how the vehicle does off-road. Toyota means business when they do off-road. It's no joke. So pretty cool. And then there's the crawl mode. Now we get into the VDIM, but more advanced. Star Safety System is ABS, electronic brake force distribution, brake assist, traction control, vehicle stability control, or VDIM, and brake override. So this is a later system. This can do a lot of stuff. So this can do a number of things, but one thing that's really interesting is it cuts engine power if the brake pedal is applied and the gas pedal is applied. So you may know back in the day there was a recall, and I got my own feelings about that, but it has a lot to do with floor mats. Customers were saying, they couldn't stop, the brakes were out of control, unintended acceleration. Well, Toyota came through and came with a new system, and they said basically, with brake override, if your brake pedal's touched, your engine power's cut. What's kind of funny is if your brake pedal switch malfunctions, it'll make your engine barely even rev up. It'll basically be at idle. So they're kind of tied in. It's an interesting thing. Now we'll jump in a little more diagnosing. So every time we turn it on, right, ABS is going to go about 3 minutes on for the bulb check. And then once we reach 4 miles an hour, it's going to do a little pump and motor run and maybe a little valving. So look, noise and pulsation are normal. They do that. If they find a fault, ABS and or brake warning lights illuminated. Like a wheel speed sensor would do just the ABS light, that's kind of yellow. Amber, really. And then if it's, let's say, like a brake pedal pressure sensor, brake fluid pressure sensor, that could actually be more hydraulic. So you may see both the amber ABS and the red brake light. The red brake light is more like a safety thing. The amber ABS light is more like well, your brakes work fine, but you may not have proper ABS type of thing. And sometimes it's both. And sometimes it's one problem that causes both. So it's kind of interesting. Now, note for you, if there's an ABS fault, what's it say? ABS is disabled. Normal hydraulic braking will function, but without anti-lock capabilities. So when we were trying to do donuts in the snow, we disconnect the wheel speed sensor so the ABS wouldn't go off, and you can go all kinds of crazy, but I shouldn't tell you that. I just did. And so this is a little over too much detail, but basically the ABS initial timing check, it's going to check each one of these valves over a course of about 408 milliseconds, and then the pump motor over another 300. So it's just saying it checks, it checks this, it checks that, it checks this, it checks that. It does a self check right after startup when you hit about 4 miles an hour. And then there's lots of warning lights. So we could have all sorts of warning lights potentially. It depends on what the failure is. So if you have just an ABS light, that would be amber, and it would be just ABS. If you have a VSC light, that tells you VSC is malfunctioning. If you have auto LSD, that's malfunctioning. But remember how the wheel speed sensors have to do with like all of these, except not the brake warning. Sometimes you can get a little bit of a prediction like, oh, I've got all these lights on except for brake. You might be thinking wheel speed sensor. But if you've got maybe just the ABS light on, maybe it's not going to be wheel speed sensor. So it's not a real important point, but if you have a failure that affects all those systems, you're probably going to get all those lights on. You're still going to diagnose it the same though. You're going to connect the scan tool, you're going to pull DTCs, and you're going to diagnose the DTCs. Makes sense because all these are based out of that skid control ECU. So it's all good. And then for example, let's say we had a C0200 front right wheel speed sensor. Trouble areas could be the sensor, could be the circuit, could be the sensor installation, could be the skid control sensor wire, could be the master cylinder solenoid, which is in the skid control ECU, right? So we're going to go to page BC59 and we're going to follow step by step by step. We can also get a little sample of the wiring diagram. So if there was a left front wheel speed sensor, we know at the skid control ECU, it's terminal 5. That's going to go to terminal 1 of the actual connector at the sensor, out terminal 2 of the actual sensor connector, and then back to terminal 6 at the ECU. So be roughly familiar with this circuit because we got a lot of work coming up. And also my other video, I walk you through a diagnosis, right? And then additionally, we got step by step, check, connect, check, measure, check, measure, get a waveform. It might have a resistance test. It might have only a sample waveform. So the diagnosis is usually pretty well laid out. It just may take some time. And additionally, we may go into the data. So if it were me, to be honest with you, and we were trying to diagnose the left front wheel speed sensor, I'm going right for data. I want to see what the wheel speed sensor reads. Is it coming up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 miles an hour? Or is it staying at 0? And if it's staying at 0, then I may jump into some more of these tests. If you understand it, you can diagnose it efficiently without doing unnecessary steps. All right. And so like active tests, for example, if you think you have a problem with a solenoid, you can active test a solenoid. We can do that. If you want to run the motor, we can active test the relay and it'll run the motor, the brake, they'll call it a ABS motor, ABS motor actuator or actuator motor and relay. We can test those. We can also use our meter to test resistance, for example. And they say don't ohm test MRE wheel speed sensor. So that's an active wheel speed sensor. That's a Hall effect. There's no resistance to check. We need to actually measure voltage, and we need to do it with an oscilloscope to get a good reading, to get an accurate reading. And then a 0-point calibration, that could be a number of different things. If it's if let's say we replace that ABS actuator, we need to do 0-point calibration. That's going to calibrate yaw rate and acceleration sensor to 0. It can clear it and calibrate it. So if we have, and we have a similar one with the steering angle, but we may not call that, we may call it a couple different things, but it could be a steering angle reset or it could be a 0-point calibration. We can even have to do that sometimes with rear air suspension on, let's say, like a nice Sequoia. We can actually 0-point that to what 0 PSI reads. So there's a few utility tests there. And then this mostly just talks about um, generic ESC. So I kind of summarized this early because Roberto asked a really good question, but basically ESC's integral part of maintaining control of an out of control vehicle, uses various sensors and the electro hydraulic control module. This one, for example, you see is not locking up. It's actually coming around a turn and it may not be fully in control. So it's, remember, ABS was for lockup. Traction was used to cut power, but this was due to skid and this was due to basically slip. And then ESC becomes steering and intention, right? That's basically what this is going to say. To prevent you from losing control of the vehicle, it's like ABS and TCS, but enhanced. And it's going to include a yaw sensor, steering angle sensor, lateral acceleration, which is going to probably be built into the yaw. It might even have a roll rate sensor, which might be built into the yaw, in addition to all the other ABS stuff. And so you can see they've added several things to that same module. And if we get even more advanced, we've added quite a bit more. So here's an example of that hydraulic control unit and the EBCM or the skid control ECU. Right. And then let's say it's a performance car with that electronic stability control. We can have it in different modes. So let's say you are about to do a track and it's rainy. You can a lot of times put this on something like a rain mode, and that's gonna cut your power, probably be a little bit less aggressive with your ABS. And that's going to hopefully get you to have better traction. Or let's say you're doing touring and it's even got magnetic ride control or something, that's going to affect your suspension. So this may affect not only brakes, it can also affect steering and suspension too. So we're veering a little bit away from brakes, but that's still the idea, right? You can put it in a different mode, and that will change the programming for your stability control. Or let's say you put it on track, that may take some of your traction control away, some of your stability control away, and leave you with basically it's more like you in the car. Makes sense. So we can actually fine tune these electronic systems if they have a mode switch. It's pretty neat. But it does get more advanced. Let's say collision avoidance. Collision avoidance, for example, is going to use all the stuff of ABS and VSC, and we're going to add new stuff. We may use radar, GPS, cameras, even other sensors, and addition of a collision avoidance computer or something similar, which is basically going to try to determine if there's a collision that we're about to have. Like, so for example, if we're coming up in this car and this is using radar, sonar, and or forward facing camera, it sees we're coming up in this car. Once we get into this range, it can gauge the distance. It may make a sound, right? It may have a light. We've even had the steering wheels that light up with an LED. I've had seats vibrate, I've had steering wheel vibrate, and I've had various different sounds. This is all warning, 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 warning. But if you go too far, that would be collision warning. But this is collision avoidance. If you go too far, brake support actually means it'll apply the brakes for you. Because remember, we got the three-way valve. We can apply. We can run the pump and motor. We can build pressure, and we can apply the brakes. Not only yell at you and beep and vibrate your butt, we can stop the car for you. So this is an extension of those same systems, just more advanced. All right. And so, and even lane departure and lane keeping, it gets a little bit into steering, but it's the same type of an idea, using those same cameras and sensors. If we're getting out of our lane, it can not only warn us, it could actually potentially make an adjustment to our electronic power steering system. So this is the direction the system's going. Here's your forward camera. We are going to do calibrations on these cameras, but they're going to be later in the semester. All right, but those are all important, and it's all leading up to this one. The system's close to autonomous driving. So autonomous driving would mean it doesn't need you even in the car. We're not really allowing that. I mean, we're basically there, but we're not really allowing it. Right. So that's some more about lane keep assist. Adaptive cruise controls are cool function. So we're using, again, sonar or radar. We could even use LiDAR too. And that's going to measure this distance. And basically, if your cruise control is on 70 and you come up on this car and they're doing 65, your car will no longer do 70 because that would result in you hitting them. It'll actually pace them at 65. It'll maintain this difference. How much? About 200 feet, 150 feet in this setting. If you don't want to follow closely, you can adjust it to maybe 250 or 300, and it'll just trail a little more. It'll do it all automatically. So that's again an extension of the systems that's leading more and more towards autonomy. And our final subject is hybrid braking. We talked a little bit about it. We'll get a little more in detail. What's different about hybrid? The master cylinder may not actually apply the brakes. The master cylinder, as you'll see in this next one, operates a little different. We got a brake actuator, could be similar. Over here, and a lot of times attached or unattached, a stroke simulator. That means you step on the brakes, this thing is going to function in a way that's going to make it seem like you're applying the calipers. And you might be, but you might not be, right? It's just going to simulate a stroke so it feels like you are. And then using all these other sensors, if you need to actually apply the brakes, the stroke simulator will knock it off and it'll let you actually apply the fluid and squeeze the calipers. But if it doesn't really need it, remember we kind of started talking about more of that regenerative braking. It's It's going to try to use as much regen braking as possible because that's going to be better for the battery, and we're not going to wear the pads. So that's a good idea. And so when it talks about electronically controlled braking, what it means, you press the master cylinder, that presses the stroke sensor, and you feel good. But you know what? It don't do nothing. It sends a signal to the skid control ECU, which will basically look at how much regenerative braking force we do. Plus, if it needs, it might add a little bit of hydraulic brake force together, and that's going to slow the wheels. The more regen force we do, the better. The less hydraulic braking force we do, the longer the brake pads will last. And the more regen braking we do, the more full our battery is going to be, the better fuel economy or the better range we're going to get. So it's blending the two together, and this actuator does all that stuff. Does all that. It's got very in-depth programming. And then we're also going to look at the brake pedal sensor, and the sensor is basically interpreting where our pedal is. Now, who thinks this is scary? What if the sensor fails? That's what Oprah said back in the day when it was unintended acceleration. The sensor fails. It's electronic. Well, check it out. We got double redundancies here. So as you apply the brakes, this is going to increase in voltage. And if you're at, let's say, a quarter application, this sensor should be at about 1 volt, and this sensor is going to be at a very different number. So this one's a little bit hard to say, but let's say you're at 50%, they should both read 2.5 volts. And let's say you're at 15%, or let's make it 20. Maybe you're at 1 volt and this one's at like 4 or 4.5. Those two numbers have to agree with each other. If those numbers agree with each other, we're chilling. If for whatever reason this one's reading 1 volt and this one's reading 3, that's going to be a brake sensor A, brake sensor B correlation. That car is going to be like practically shut down. You're going to lose power. You're going to lose all sorts of stuff. So it's not as simple as, oh, the sensor went bad. It have to be sensor A that went bad and sensor B that went bad, and they happen to go bad in a way where the two happen to agree. That's not going to happen. It's just not going to happen. It's just not. It's really just. I'm not going to say impossible, but if you're worried about that, you shouldn't even go outside, because you might go outside and you may get hit with a part that fell off of an airplane, or a bullet that someone shot up in the air to celebrate something is probably going to land on you. It's just the probabilities are so low. So this is a good system. That's what we mean by redundancy. Additionally, we've got the varying stroke simulators. Newer ones, we're going to have stroke simulator on the actuator. We used to have them separate. We got quite a few different actuators. So 04 to 09 Prius, the brake actuator was over on the side. It looked like more like an ABS unit, we may say. Highlander was similar. 10 Prius and up, we've gone to the whole combined, right? This is where things have been going, for better or for worse. Sometimes mostly better, but sometimes worse. If one part goes bad, it gets the whole thing. And you guys got to do one. That was fun. And then we do have a power source backup unit. So here's what that's for. Like everything, vacuum, if we lose vacuum, we've got a check valve, so we still have some brake force. Electric boosters, if we have a loss of power, we still have the accumulator. Well, with this, we actually store capacitors, store electricity, and that will allow the electric brake actuator motor to run so that it'll still give us brake assist. So even if a Prius loses all power in some horrific accident, these capacitors will give us still enough power to run the motor and get good brake assist. So it's pretty good. When you're about to work on it, you're actually supposed to power it down and wait 5 minutes for the capacitors to discharge. That's the service procedure. Again, follow the service manual. And last but not least, again, it's hybrid stuff. So you'll be, if you're going to do work on anything with orange cables, remember we got to go back to safety, disabling, taking the high voltage system down, etc. Just follow the procedure. Okay. Boom. There you are.